Alright guys, let's take a look at today's lesson. This is optimization day 2. So we've already talked about what optimization problems are, how to solve them. We're going to solve our second one together. Now this particular type I think is one of the most difficult to do because it doesn't involve like a volume formula or something like that. It actually involves time. We don't have a lot of problems that involve time, so it's just a little different for us. So let's kind of walk through this one. I did have one like this on your daily work from day 1, that number 3 that we skipped, and so I would encourage you to go back and work it. I mean, not while we're doing daily work today, because I have another one for you on the daily work for today, but just for practice I would encourage you to go back and work that one. So we have a man launches his boat from point A on a bank of a straight river 3 kilometers wide and wants to reach point B 8 kilometers downstream on the opposite bank as quickly as possible. As quickly as possible. What is that telling us? We want to minimize time. We want to minimize time. So before don't want to keep going, I want to stop and kind of record what we have learned so far. So we have a stream. We have point A where he launches his boat. See, the stream is 3 kilometers wide and he wants to reach point B, which is on the opposite side, and that is 8 kilometers downstream as quickly as possible. So far that's what we have going on. We all okay? Okay, so he could row his boat directly across the river to point C. So this point is C. And then run to B. Or he could row directly to B. Or he could row to some point D. We'll say this is D. Between C and B and then run to B. Okay. So that's a lot of information right there. They're telling us 3 scenarios. Right, 3 scenarios. He could row straight across and then run this distance. He could row straight to where he's going and never run. Or he could row to somewhere in between and then run. So he's got lots of options. He's got 3 options basically. Alright. And let's see. So if he can row at 6 kilometers per hour, which is a rate. So I'm going to write it as a rate. Rowing, I'm going to write, well, just write dW. dW dt equals 6. And he can run dr dt equals 8. Those are kilometers per hour. Now, some students seeing those rates would, I hope not, but maybe think that this is a related rates problem. It actually isn't a related rates problem, although it has rates in it, which makes, again, I think it makes it one of the more difficult problems that we would work. What we have to think of is what kind of an equation do we have that relates distance and rates and time, right? Yes, our old favorite, distance equals rate times time. That's the equation that we're going to use here. Okay, and the rate is actually in the equation. We don't have to take the derivative of it. It is actually in the equation. Distance equals rate times time. So it isn't a related rates problem. It's an optimization problem. Okay, so that's the equation we're going to use. But I need a little bit more information before I start using that equation. I need some more on this diagram. I need some variables, like some distances. So what I did is, this is so he can row across and then run. He can row to D and then run, or he can row all the way to B. So I'm calling this distance right here X. The distance between C and D is X. Okay, with me on that? That distance between C and D is X. So if I want a variable to relate this distance between D and B, how would I come up with that variable with respect to X? 8 minus X, right? Because I have the total distance is 8, and I take out this part right here. So this would be 8 minus x. Okay, so and I had a lot of confusion in the last class about domain. So let's talk about domain. Let's talk about what our options are. What if, so domain has to do with the variable that we're using in our equation. This is going to be an x. We're going to use x's in our equation. And I want my domain, this does have a domain, I want a domain for x. What would happen if x were 0? He would be going straight across. So that's really one of the options they want us to explore, right? If x is 0, he's going straight across. So that is actually the first option that they talked about. Row straight across, x is 0, he runs the whole way. Okay? What if he goes rows straight to b? What would my x value be? It would be 8. This right here, this distance right here. If this moved all the way down here, my x value would be 8, right? My x value would be 8. And so this deals with the other extreme that they wanted us to check out, is if he rows the whole way and doesn't ever run, that would be this one. So you can see, hopefully you can see that we are setting up to do a candidates test. We're going to have to check the endpoints, which are the two extreme things that could happen, rowing straight across and running the whole way, or rowing the whole way. But we also have to come up with an equation that will help us find critical numbers for this middle kind of scenario where he rows to somewhere between C and B. Okay, with me? Now, what we're wanting to minimize is time. So what I'm going to do is I'm going to actually solve this equation for time. This will make our life a bit easier because that's what I'm minimizing. I'm minimizing time. So let's solve it for time. So time is going to be distance over rate. Now we really have two separate things going on, the running and the rowing. I really need a fraction for each one. Okay, I want my time. My time is going to be equal to the, running fraction plus the rowing fraction. Okay, so let's work on the running fraction first. I think that one is a bit easier. All right, on our diagram, what represents the running part? What distance? I'm looking for, so I want to put a distance there, 8 minus x. 8 minus x represents the part that he runs. That's this piece right here. And we are given a rate for how fast he runs. And that was, what was it? That was 8. Okay, plus. We all okay with the running fraction? Okay, let's look at the rowing fraction. So we need, okay, again, the top of our fraction is distance. So we need something to represent this distance right here. Let's see, we have the distance, we have this is x, and that's 3. Ideas on what we could use to represent? Yeah, our friend Pythagorean theorem, right? We can use Pythagorean theorem here. And so we get x squared plus 3 squared equals, and we'll just call it, I don't know, rowing squared, which I used a w. So our rowing is going to be square root of x squared plus 9. So that's the distance that he's rowing. So that would go here, square root of x squared plus 9. And the rowing time was 6 kilometers per hour. Okay, so that's our equation that we're going to use to come up with our critical numbers for this middle kind of scenario, where he's going to row to somewhere in the middle. Okay, so I would, before I took the derivative of it, I would kind of, pretty it up a little bit. So 8, I would take this and turn it into 2 fractions or 2 entities. So 8 over 8 is 1 minus 1/8 x. I think that's going to be easier for me to do the derivative, at least visually, plus 1/6. And I'm just going to go ahead and write this in exponential form so that I don't get, perhaps make an error. All right, so now we're ready to take the derivative. So the derivative of 1 is 0. The derivative of negative 1/8 x is negative 1/8. And then we do the derivative of this little guy. We bring the half down. Half times a 6 is, what, a 12th. Copy, paste the inside, subtract 1, multiply by the derivative of the inside, and there's our derivative. Alright, so let's get it prettied up a bit so that we're going to actually have to find the zeros, so that's going to take just a little bit of algebra. So the negative 1/8 I'm kind of happy with, that's fine. Hopefully we see that 2 and the 12, that will reduce, right? 2/12. The 2 is going to go away just to 1/6. I'm going to have an x left in the numerator, and then a 6 times the square root of x squared plus 9. Okay, all good. So my job now is to find a common denominator and add that together. The common denominator between the 6 and the 8, what's the smallest number they can both divide into? It'd be 24, right? So I'm going to have, and I'm doing this kind of all at once. Hopefully we should be fine with me finding the common denominator and putting it together all at once. If not, please do it in pieces so that you're comfortable with it. So that's my common denominator. The first piece, I'm going to need that negative 1 needs to be multiplied by what? By 3, and the radical squared plus 9, and then plus that x needs to be multiplied by what? By the 4. So there's a 4 in there, plus 4x. Alright, so let's look at the denominator. We're setting up our critical numbers now. Is there anything that could make that denominator 0? No, even if I made x negative 3, that wouldn't work, right? Because they would square it first and then combine it together. So it's impossible to make the denominator 0. So I don't have any undefines here. All I have are zeros. So we set the numerator equal to 0. Then I solve. I move the 3 and the root over. The technique that we're going to use here is squaring both sides, which we have to always be cautious with because why? It could create extraneous solutions. So not that it always does, it just could. We just need to pay attention. Okay, so we're going to square both sides. We get 9 times x squared plus 9 equals 16x squared. I distribute combined like terms. I get 7x squared minus 81. I solve for x. X squared is 81/7, so x is plus or minus. What do we have? 9 over root 7. Of course, we can't have the negative, can we? Alright, so there's no, we don't need to do a sign chart because we have to do the candidates test. I mean, if you want to do a sign chart, you can. It'll just show you whether that is a relative max or min, but we need to do the candidate test anyway. So our candidates are t of 0, t of 9 over root 7, and t of 8. Those are our candidates. And you would have use of a calculator. You would just substitute those into where? Where do they go? Yep, our original equation over here, right? We're using our original time equation over here. This little guy right here, that's where we're subbing in. So I sub a 0 in, and I get 1.5. I sub 9 over root 7 in, I get 1.3307. I sub an 8 in, and I get 1.424. Okay, so which one is the winner? The 9 over root 7. This means that, so let's make sure we understand what it means. What does this 9 over root 7 stand for? The x, it stands for how far down, right? He should row, where he should row the boat to, how far in with respect to where the distance from sea. So, or downstream, they're talking about that being downstream. So he would row 9 over root 7 kilometers downstream, and 9 over root 7 is approximately 3.402 kilometers. Okay, and as far as justification, you can say reference to candidates test, by candidates test. Okay, how are we doing? Is everybody all right? And like I said, this is I think it's the hardest optimization problem, this type of problem. If you can get this one down, that'll be great. All right, and you have a couple to practice.